Welcome to Ask and Learn.
This is the answer to Chapter 20, problem number 79 from the Smith Organic Chemistry textbook. And this problem says that lithium tri-sec-butylborohydride, also known as L-selectride, is a metal hydride reagent that contains 3 sec-butyl groups bonded to boron. When this reagent is used to reduce cyclic ketones, one stereoisomer often predominates as product. Explain why the reduction of 4-tert-butyl cyclohexanone with L-selectride forms the cis alcohol as the major product. Okay, and so some things that we need to keep in mind. So L-selectride is basically a lot like sodium borohydride. So it's lithium tri-sec-butylborohydride. So it's a boron, a central boron with a hydrogen on it, and then 3 sec-butyl groups. And so that whole system has a negative charge, and then it's counterbalanced with a lithium ion, so a lithium with a positive charge. So it's a lot like sodium borohydride, except that in sodium borohydride, the central boron just has 4 hydrogens on it. So the difference here is that the 3 sec-butyl groups on the boron make this boron a lot bulkier. So let me actually just draw it. So it's going to look like this, basically. So we have a lithium ion, and then we have a central boron ion that's going to have a negative charge on it. And then we have 1 hydrogen and 3 sec-butyl groups. 2, 3, 4. Okay, and again, these 3 sec-butyl groups are here basically just to function as bulking agents. So they serve to make this a much bulkier molecule. And the reason that that's important is because it means that in a substrate that's sterically hindered, the boron is only going to be able to deliver its hydride to the less hindered side of the system. And so that's the utility of this reagent. It's selective because it delivers exclusively to the less hindered side of a substrate. And so what that means in practice or in actuality, so when we look at this molecule, our starting material in a chair conformation, okay, and so what we'll see is that obviously the T-butyl group is going to be equatorial because we want, or the molecule is naturally going to assume a conformation where equatorial groups or bulky groups are in equatorial positions because that minimizes steric strain. So then we'll have our ketone here. Okay, and the L-selectride is, so we'll just call this R3BH. Put the negative charge here on the boron. So this is basically going to come in and deliver this hydride, and it's going to preferentially deliver from the less hindered face. So the less hindered face is going to end up delivering the hydride such that the resulting hydrogen is equatorial. And that's because there's a big T-butyl group as well as the rest of the ring blocking axial approach. And so we end up with this. Man, getting some serious lag. Okay, so we end up with this, where our alkoxide that we form is here, and our hydrogen has been delivered so that it is now equatorial. And once we work that up with water, we end up with our axial alcohol. Okay, so there we go. You can see that the alcohol, pardon me, the alcohol being axial here on this top carbon, and the T-butyl group being equatorial there on the bottom carbon across the ring, end up making these two groups cis to one another. And so this is why we get the cis product here, because the L-selectride can only deliver its hydride from the less hindered face of the ring. And so in this case, it delivers that hydride so that the resulting hydrogen ends up being equatorial, and the resulting alcohol ends up being axial. And so, as the answer so often is, it's sterics. Yeah, okay. And so that's the answer to chapter 20, problem number 79.